Um, my brother is a programmer, and my sister is a network engineer. So, yeah, and I'm just a user. But if if they make it, I'll try to use it. Okay, all right, I think we're back on that. Okay, so this is the complement rule. Okay, so this is how we're going to use it. Okay, everybody got that in mind? All right, let's look at another example. Provide a written description of the complement of the given event, then find the probability of the complement of the given event. So say what the complement is, then we're going to find it. Okay? So when a couple has 5 children, none of the 5 is a girl. The complement, let's say G, is the event of no girls. Okay? In 5 children. Then the complement is what? At least one girl. Very good. Okay? So if I'm interested in the probability of at least one girl. Okay? This is going to be 1 minus the probability of 0 girls. And I think it's a good idea for us to remember of how many. Okay? And so when I say 0 girls of 5, then we must have what? 5 boys. Very good. So I'm writing this out because this is how I have to think it through in my head. The probability of 5 boys. Okay? And so we get, this is where the multiplication rule comes in. We're talking about what? Boy and boy and boy and boy and boy. And so we ask ourselves, are these events dependent or independent? Independent. Okay? So it's going to be the probability of a boy raised to what? The 5th power. Excellent. All right, I think y'all were here last time. That's good. Okay, so 1 minus 1/2 to the 5th power. 1/2 to the 5th is 1 over 32. So we get 31 over 32, and that's some decimal, okay, that you could state. But the probability of at least one girl would be 31 over 32. Questions about that? How did I get the half? Well, you could either be a boy or a girl. Each child, yeah, assuming equally likely outcomes of boys and girls. That's where we got the 1/2. Okay, other questions? All right, if you do that out on the calculator, it comes out to what? 0.9, 0.96, what is it? 87, okay. So we'll say 88. All right, is that number surprisingly high to you? Yes, okay. But you have to stop and think about what at least one includes. It includes every case where we would have 5 children and have exactly 1 girl. Then we got to go back and look at exactly 2, and then exactly 3, 4, and 5. It includes every outcome except for 1, which would be boy, 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 boy. No girls. Okay, so when you think about it that way, then, you know, at least 1 girl, that's every outcome except the 1. Okay, so it's not so large after all. Okay, let's look at this next problem. A statistics student plans to use a TI-84 plus calculator on her final exam. From past experience, she estimates that there is 0.92 probability that the calculator will work on any given day. Because the final exam is so important, she plans to use redundancy by bringing in 2 TI-84 plus calculators. What is the probability that she will be able to complete her exam with a working calculator? Okay, so probability of working calculator. Or I guess, well, yeah, we'll say that. All right, well, in statistics, I don't mind, but I think it's difficult. I don't know. But anyway, how does this relate to at least one? At least one works, right? We're talking about the probability that at least one works. Now, the beauty of this complement rule is it really does save us some time. Like I was saying before, we don't want to spend time trying to calculate, the probability of exactly one girl in 5 plus the probability of exactly 2 in 5 plus 3 plus 4. We were able to calculate just one thing and subtract that from 1. Same thing here. If we talked about at least one working, that would be the probability that the first one works, but the second one doesn't, plus the second one works, and the first one doesn't, or they both work, right? Instead, we're just going to use the complement rule and say 1 minus the probability of what? 0 working. Okay? And again, I think it's a good idea to remind yourself of how many? 2 calculators. And so if 0 of them work, that means what? She doesn't fail, but they both fail. Okay, probability of 2 that fail. Okay? If 0 of the 2 work, then they both must fail. And so, again, we come back to the multiplication rule. We say fail and fail, right? Are these independent? If she's smart, yes. Okay, it's no need to take 2 calculators and plan to share batteries. That's not going to help. So, hopefully, if we're really having this redundancy, they're 2 independently working calculators. So, it's the probability that the first one fails, which is what? 0.08. There's a 0.92 probability that it works, so that means the probability of it not working is 0.08, and we're going to do what? Raise it to the second power. Because we got, okay, it comes out to what? Or 1 minus that is, that's okay. 0.9936. Very good. Questions? Okay, we had a 92% chance that the calculator would work. So the complement of that would be it doesn't work. 1 minus 0.92 is 0.08. Yes? Well, that's the rule. I mean, to me, I have to do this. It's hard for me to jump from here to here. So, yeah. I mean, this is really more thinking through it or whatever. Okay, yes. That's where we had to go. Sometimes I think it can be difficult to get there without going through the step, but, yeah. Okay. At least, yeah, one of the calculators working, which is good, right? She should be okay. All right. We don't know. I don't know. Okay. All right. So here's another one. This one's really kind of tricky because of the language. So I'm going to kind of stand back because maybe I messed it up when I did it. But we want to find the probability. It says it has been found that 40% of all people over the age of 85 suffer from Alzheimer's disease. If 3 people over 85 are selected at random, find the probability that at least one does not suffer from the disease. Okay? So probability, at least one. What do we want to call this person? Do we want to say does not suffer? So, at least one, let's call them okay. How about that? Okay. All right. And so the complement then is what? 1 minus probability what? We'll say 0. Okay. All right, and that's of 3. All right. So if 0 of them are okay, then that means what? All 3 have the disease. So 1 minus the probability, 3 with disease. Okay? And so we're talking about disease and disease and disease, which means multiplication rule. And we ask ourselves, are these things dependent or independent? We're going to treat them as if they're independent. Okay? We talked about that last time. So we get 1 minus the probability of the disease is what? 40%. So 1 minus 0.4 raised to the 3rd power, which comes up to what? Okay, 0.936. Okay. So probability that at least 1 in 3 doesn't suffer from the disease is so the answer is 0.64? Okay. And what are we doing now? That's the final answer. Yes? Oh. 1 minus, yeah. Okay. 0.936. Okay, 0.936 is right. Y'all just trying to mess up my video. That's what's going on. Well, but we converted that to with disease. So if 0 of them were okay, then we have to. Okay. All right. Very good. Questions. You got to pay attention to the, little pieces or whatever. Okay. Questions. All right.
So can that's 0.936
At least 1 of the 3 would be okay, not have the disease, which is actually encouraging. Okay. Questions. Excellent. Alrighty. Just maybe a couple of more. According to the FBI data, 12.4% of burglaries are cleared with arrests. A new detective is assigned to 5 different burglaries. What is the probability that at least one of them is cleared with an arrest? Okay, so we're interested in probability of at least one cleared. Okay, and so the complement of at least one is what? 0 cleared. Okay, so 0 of them are cleared, then we must have how many that are uncleared? 5. Okay, 5 uncleared. And, we're going to have to assume that these are independent because they gave us 12.4%. That number should be from a large number of observations. So it's unlikely that we'd select the same one twice. So we get 1 minus probability of uncleared is going to be what? Okay. Probability of uncleared is 0.876. We have 12.4% of burglaries that are cleared. So 1 minus 0.124 or 0.876 would be uncleared. And so we get 1 minus 0.876 raised to the 5th. the final answer is I got 0.4842. Okay, 0.4842. Okay, so roughly the probability that at least one of them is cleared with an arrest is 0.4842. Okay. All right. What is the probability? We already, I think, found this. Maybe not. What is the probability that the detective clears 5 burglaries with arrest? Okay. How are we going to solve that? We'll go back. Is this an at least one kind of problem? No. It's just what? Okay, this is more of a multiplication problem, right? We got cleared and cleared and cleared and cleared and cleared. That's multiplication. And we already said they were independent, so it's what? To the 5th power. Okay, 0.124 to the 5th power. Very good. All right, very good. Okay, so what should we conclude if the detective clears all 5 burglaries with arrests? Okay, that was a jump, but okay, baby. He's very good. Or maybe we could say they gave him easy cases or whatever. Okay, but it's really unusual that that would happen. Okay, he might be crooked. Okay, as was suggested. All right, questions about that? All right. All right, let's see. Maybe one more, then we're moving on. Oh, there's the birthday problem. Okay, 2 more. All right, the birthday problem. Well, let's do this one, and then we'll do the birthday problem. In a lab, there are 8 technicians. 3 are male and 5 are female. If 3 technicians are selected, find the probability that at least one is female. Okay, at least one female. And that's of how many? No, something else. How many are we selecting? Of 3. Okay, it says if 3 are selected. So of the number that we're selecting. So of 3. Okay, so probability at least one is equal to is female. We're going to say 1 minus the probability that 0 are male, which means what? 0 are female, so that means we have what? 3 males. Okay. And so we've got male and male and male. Are these events dependent or independent? And this is a small sample size. So in this case, we would say dependent. Okay, we only have altogether 8 technicians. So, and we said we sample assuming it's without replacement, right? And so if I take one out, that's going to greatly change this sample space because it's a small sample space. So just kind of reminding us about that multiplication rule for dependent events. We get the probability that the first one is male. Yeah, let's just write this out just so we remember. Times the probability that the second is male, given that the first was male, times the probability that the third is male, given that the first and second were male. And so the probability that the first one is male is going to be what? Not 5/8, is it? 3/8. Okay, 3/8. And then the probability that the second is male, given that the first was, is 2/7, and then 1/6. Okay? So we get 1 minus 6 over, well, the 6 is canceled. So 1 minus 1 over 56, or 55 over 56, which comes up to some number. Okay, questions about that? All right. Last one I want to look at for now, regarding at least one anyway, is this birthday problem. And most of you by now should have, I think, already done your little birthday experiment. Maybe that was last weekend. I can't remember. But anyway, well, hopefully you're going to do it soon. And I don't know, based on what you've done so far, do you think it's likely that among 25 people you would have at least 2 that have the same birthday? Okay, all right. That's about right. And we're going to see if we can calculate that here today. Okay, all right. So, very good. Very good. 3 that have the same birthday. Okay, so
4 out of 50.
okay, 4 out of 50. So, like, if you divided them into 2 sets of 25, what'd you do? You had 2.
Yeah, but one of them was 4 times. Like 4 people out of the 50 had the same birthday.
Wow.
Yeah.
Okay. Wow.
They were all June 11th.
And were they related?
Nope. They were
That's
all on
amazing.
Facebook.
Okay, cool.
I thought it was like when I was going through, because I just posted a status and like I was reading all the comments,
Mm-hmm.
and I was like, hold on, I swear I've already seen this birthday, and I had 4.
Excellent. Okay, very good. So it's even in your experiment, it's not as unusual as you might think. You can see that already. So how would we calculate that using what we've talked about? Well, we're looking at the probability of at least 2. Okay, which we, don't get caught up by that. Basically, that's the same thing as saying we got at least one match, right? At least one match. So let's just call it that. At least one match. Okay? Well, we certainly would not want to address this head on. We'd have to look at the probability of having exactly one match, and then the probability of having exactly 2 matches, and then exactly 3 matches. And then what about the case where we got 2 who match over here and 2 that match over there? We'd be there forever trying to do it that way. The easiest way to do this would be to use the complement rule. So 1 minus the probability of 0 matches. Okay, and remember the other day where we talked about Google hiring people on the same day? Did we do that problem in here? Okay, so we're going to use a little bit of that when we were trying to match people up the other day. Okay, if we have 0 matches, all right, then the first person's birthday could be any day, right? Okay, so he gets his pick. 365 over 365. But then the second person's birthday could be any day except for what? First. So he only has 364 over 365. Now when I get to the next person, he can't choose, his has to be something other than these first 2 days. So we get 363 over 365 all the way down to 341 over 365. Okay? And there's some nifty ways to calculate that that we're going to talk about hopefully before we leave here today. But if you did it all out and subtracted and everything, it's approximately 0.56. Just about a 56% chance that you would have at least 2 people in amongst 25 that have the same birthday. Okay? So not so interested in the number, and this problem is a little complex, but just to kind of put a tie-in to what you did online, and also wanted you to think about how we're still using that at least one principle to get us the answer that we wanted. Okay? Very good. Excellent.